Okay, so coming back, the last lecture we did the definition of field and we saw the properties of what does field mean. So these were all the properties: that's commutative, associative, distributive, additive inverse, multiplicative inverse, and then there is an additive identity and multiplicative identity. Now, in this lecture, we will be looking at an example of a very popular field. So let us take a line, the number line, and we can call this number line the real number line. So that is 0, 1, 2, 3, and with that we even have -1, -2, -3. Basically, this line is the set of all real values. Okay, so we often call this the real line and the real number or line with the real numbers. So there are infinite number of numbers in this line. Even between 0 and 1 there are infinite numbers. That's what real number means. So we have to know that, is this a field? So if we see that any number, any two numbers on this, suppose 0 and 1, if I add 0 plus 1, so 0 plus 1 equals to 1 plus 0. So additive property is satisfied, right? Then we have 0 into 1 plus suppose 3 equals to 0 into 1 plus 0 into 3. So that's also satisfied, that is the distributive property. Then we have any two numbers like let's take like 2 into 2 plus 4 plus 5 equals to 2 plus 4 plus 5. So that's also right. Then there is always, for any number on the real line, suppose for 1 there exists a -1 such that plus 1 minus 1 equals to 0. So additive inverse exists for every number alpha, suppose 2, there exists an half such that plus 2 into half equals to 1. So multiplicative inverse also is available here, and with that we also have the additive identity, that is with 0 we add it becomes the same number, and we have the multiplicative identity that if we multiply it with 1 then we get the same number. So this real line can be called a field. So this is a field of real numbers. Now the interesting part here is that the field, there is a very useful, or we can say like there is a very interesting thing here, that is, suppose we have that S field and we have the set S, and in the set S we are having elements like v1, v2, then we have v3, v4. Okay, so let's take four elements, v3 and v4, and we have another set, a field, not a set this time, this is a field, although every field is a set still. That is, we are having two values in the field, alpha 1 and alpha 2. Now if we do it like, if we take the values v1 and v2 from this set, so and we add them, so v1 plus v2, and we take alpha from this set, so it can be alpha 1 or alpha 2, in general we are taking it as alpha. So alpha v1 plus v2 is alpha v1 plus alpha v2, we get this one. Now if this thing itself belongs to that same set, if this belongs to this set, then it is something. Same with, if we take another element like alpha 1 suppose from here, and we take v4 from here, and if we multiply them it becomes alpha 1 v4, and if alpha 1 v4 belongs to this set itself, let us just make this a little bit less messy. So, and let us change the color, actually we can use orange for this. We actually, if it belongs to this set only, So what can be called that this set S, the set S is a vector space over field F. So we have to understand this thing in more detail actually. So we have to understand here a very important thing. So a set V is a vector space over a field F. So it is a vector space, I'm writing vector space as Vs over a field F if vectors come from V and scalars come from F. Okay, so we can write as V is a set of vectors and F is a set of scalars. And then if there is a scalar multiplication, that is F cross V, the mapping is always to V, the set V. So what we exactly did here, that operation from this set with this set, any operation with from a field F, so any operation from here with this set, any operation you do, it will belong to this set. That is, then this set, this S set, or in here we are writing it as V, it can be called as a vector space over the field F. So that is one part, and then we can move on to the next example. Like we can always say like Rn, suppose. Now Rn is the n-dimensional vector, and we have to understand what do we mean by n dimension. So, and this is n-dimensional vectors. So Rn is a vector space over R. Similarly, Cn, that is complex numbers, n-dimensional complex number, is a vector space over V, over C, the space, the field of complex numbers. So we can actually prove one of them. So let's prove them. So okay, the vector space, actually the things, the properties which are defined by the vector space or which are satisfied by the vector space is the same as the ones which are satisfied by the field. So they are closed under addition, they are closed under scalar multiplication. Then there is an additive identity, there will be additive inverse, there will be distributive, there will be associativity, and there will be an identity scalar. So that is one part. So there is an example which we are talking about, that is Rn is a vector space in R, and we need to prove this. So as we know that, okay, first we need to know what is Rn. So R is a set of one single values. So those are the scalar values like 1, 2, -1, 0.33. These are the one dimensional values. When I talk about R square, these are usually x1 and x2. So those are two dimensional values on the coordinates, like we can call it like 1 comma 3 or 2 comma 5 or 3 comma 4. These all are belongs to R2. R3 means three dimensional, so that is a x1 x2 dot 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 x3, sorry, not x. So these are three-dimensional vectors which have three dimensions, so we can call it like XYZ plane. So 1 2 3 is one of them, 4 5 2, like this we can actually have infinite number of vector vectors of R3. Now above this we can't visualize because this is in 1D, this is in 2D, and this is in 3D. But beyond this we can't visualize, so there are R4, R5, and in machine learning we actually deal with state spaces with Rn, that is n dimensional. So there can be R31, that is 31 attributes, and we will be doing this later. But we are having Rn means n dimensional vector space. That means there are n coordinates, so that's an n dimension. So n can be anything, it can be 5 6 10 15 20, any number, any infinite numbers also. So Rn is a vector space. If we need to prove, we can denote it like x1 x2 dot 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 xn with xi belongs to R. So every element belongs to R. That we have to ensure that, because these are at the end like 1 2 and 3. So 1 is a belongs to R, 2 belongs to R, 3 belongs to R, but the whole thing belongs to R3. So it's the same thing. So x1 belongs to R, x2 belongs to R. Thus in general xi belongs to R. So if we do a vector addition here, in vector addition we can find out that Rn, that is not, let's not put it like this, let's, we can do it like x1 x2 dot 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 xn plus another vector we take, that is y1 y2 dot 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 yn. This equals to, we will find out, it is x1 comma y1 x2 plus y2, not comma, x2 plus y2 dot 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 xn plus yn. And this can be found out by the coordinate geometry formulas, that if you take a specific displacement along the x-axis and then a specific displacement along the y-axis, for then the total displacement is the sum of the displacement of the x and the y-axis. Same with the scalar multiplication. So we can actually scale vectors, and we can say it like, for alpha belongs to R, for all alpha belongs to R, the alpha x1 comma x2 comma dot 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 xn is equals to alpha x1 comma, I don't know why I keep writing a plus, alpha x2 comma dot 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 alpha xn. So we are actually scaling the vector with the length alpha, up to a length alpha. And we can actually verify other axioms also. So we can basically, how are we doing this? We have to understand that vector addition. So what we did here was Rn was x1 x2 dollar, where xi belongs to R. So if xi belongs to R, then this stays in that same vector space. So x1 x2 x3 y1 y2 dot dot yn. So if we add x1 plus y1, this number also belongs to R, this number also belongs to R. So we can tell that this full thing, the full last, this belongs to Rn, right? So then at vector addition is successful, that Rn plus Rn gives you Rn. Similarly, scalar multiplication, this belongs to a scalar, is suppose this belongs to R, and this full thing is belongs to Rn. So R cross Rn, you are still getting an Rn. So that is the vector space Rn. Similarly, you can also prove other associativity rules and commutative rules and additive identity, that is the zero vector. There is always a zero vector which you can add with any things, any vector, to get that same vector, and that same vector also belongs to that vector space itself. So like this we can prove every axiom, and this is therefore Rn is a vector space in field are. Similarly, you can actually try in home to prove that this is a kind of homework that you can do, that Cn or complex numbers, n dimensional complex number is a vector space in field of complex numbers. And every proof will be same as what we did here, exactly same. You just here you're just dealing with the r dimension n dimensional real numbers, there will be dealing with the n dimensional complex numbers. So that's all about today, and tomorrow we will be doing the next lecture. We'll be actually looking at the associativity, and then after that we'll be looking at the basis of a vector space, what exactly is the meaning of basis, and then we'll do the spans and null space and range space.